So we had almost completed entropy, right? What was important was predicting signs of delta S. Just a second, let me. So we did trying to figure out delta S. We learned how to measure delta S, the entropy of the product minus the entropy of the reactant, and then just a second. And then the last thing that we were doing was we were doing Gibbs free energy. So we were at this point. This one. So we were at this point, Gibbs free energy, and Gibbs free energy was the total energy that is available to a system. What that basically meant was that if you have a system produces energy in two forms. One of them is the enthalpy change. It's the heat energy that is produced. I told you that if you burn petrol, it will produce a certain amount of heat energy, and the other energy is the energy that is created, or the work that is created due to an increase in disorder, which was that if you burn petrol, what happens is that a lot of molecules are created, and those molecules are going to create a lot of entropy disorder, and the piston will start to move up. So that was another thing. Like if you have an explosion, if you have a disorder being created, so when disorder is created, work is produced. And I told you how to measure that work. Entropy change was the work that is produced at a particular temperature by a particular system or a substance. So if I want to figure out what the work is getting produced, I will rearrange the formula, and I will just write it as delta Q being equal to minus T, or temperature multiplied by the entropy change. So the work that is produced due to entropy change is the temperature multiplied by the entropy change, and the work that is produced due to enthalpy change is delta H. So that was what Gibbs free energy was. TK, this is what we did yesterday. Is this clear? This thing over here, is this clear? Is this part clear?
Yeah. Yeah.
Right. And I told you, and remember, this was a big, this is a major point, because most mistakes happen over here. And that was that I told you Gibbs free energy is kilojoules, enthalpy change is kilojoules, while entropy change is in joules. So everything, make sure the units are consistent. This is a very important point, because most questions you're going to get them wrong because of this simple thing, that entropy change values are given in joules. So make sure you either have all of them in kilojoules or all of them in joules. Otherwise, this equation will not work. Then we talked about Gibbs free energy. I told you that if it comes out to be a negative value, that means the system has excess energy. It's giving out energy. So that means it doesn't need energy from outside. So this one is spontaneous. It's feasible. Vice versa, you've got delta G being positive. What does that mean? It means that the system needs energy overall. It's an endothermic. It's the whole system it requires energy. So it won't happen. The reaction will not happen. Whatever is happening is not going to happen. Why? Because unless you give it energy, nothing will happen. So we did an example, and I told you that I gave you an example that how to use delta G to predict whether the reaction is going to happen or whether it's not going to happen. And I'm going to do another example. Let's say I have this reaction, and the reaction is, let's do another one. So the reaction is liquid water, and that liquid water, I want to freeze it. So can you tell me, is it a spontaneous reaction or is it a non-spontaneous reaction?
Non-spontaneous.
Now remember again, it depends on the temperature. Is it a spontaneous reaction at minus 100 degrees centigrade? Like if the temperature is minus 100.
Yes.
Yes.
Then it's spontaneous.
Then it's going to be spontaneous, right? So everything depends on the temperature. So, and if the temperature is 1000 degrees centigrade, then this reaction is not going to happen. It's going to be non-spontaneous, right? So it all depends on the temperature. You can't really say whether the reaction is spontaneous or non-spontaneous until I give this information that what is the temperature. So to sum this up, this one is spontaneous at low temperatures, and so spontaneous at lower temperatures, and it's going to be non-spontaneous at higher temperatures. At higher temperatures, this is not going to happen. This reaction is not going to happen, which means that spontaneous means that the Gibbs free energy is going to come out to be less than 0 or negative, right? And non-spontaneous means that the Gibbs free energy is going to come out to be endothermic. It's going to be higher than 0. It would need some form of work. At higher temperatures, it would be very hard to actually turn it into solid ice. So I'm going to use the equation now to exactly figure out the same thing. So delta G is equal to delta H minus T delta S, right? So what do you think is the enthalpy change of this reaction, endo or exo? Freezing ice, is it an exothermic process or an endothermic process? Liquid to solid.
Exo.
Okay, that's exo, right? So that means that is negative. Entropy change. What about entropy change of this reaction? Is it increasing disorder or decreasing disorder?
Decreasing.
It's decreasing, right? Because a solid is being produced. So that means delta S is negative. There's less disorder, right? So that means both values are negative. Is this clear that both of them are negative? Is that clear? I mean,
No, sir. Can you please explain for delta H?
Liquid, I mean, changes of state, liquid to solid. What is it? It's exo or endo.
Okay, right.
Okay. So, I mean, this is, we just guessed it by looking at the reaction. We were able to figure out that delta S and delta H have these signs, right? Now I'm going to use these signs, and I'm going to try and figure out the same thing. We already know this thing. So I'm going to try and figure this out using the equation. So delta H is negative, right? And delta S is also negative, right? So what would this thing become? Because there are two negative signs now, right? Because it's minus T times delta S. So it's minus T times a negative value, right? So this thing would actually become positive. Is that clear? That enthalpy change was negative. Entropy change was also negative. But since you have a negative sign in front of it, this would actually become positive, right? So one of the terms is negative, the other one is positive. Is this clear?
Yes.
So now the next thing, if I want to make delta G negative, because delta G negative means the reaction is going to be spontaneous, right? It will happen on its own. So if it's negative, that means it's going to be spontaneous. So if I want to make it negative, one of the terms is negative, the other term is positive. So I need to make the positive term bigger or smaller. If I want to smaller, right? Because the negative term would be bigger in size, the positive term would be smaller in size. Hence, the overall thing would become negative, right? So I want to keep the negative term bigger and the positive term smaller. How can I make it smaller? T should be high or T should be low? Higher temperature or lower temperature?
Low.
Low, right? So T should be low. So if I want to make it a negative value, if I want to make delta G negative, I would have to keep T as low as possible. And this is exactly what we figured out over here, that the reaction is going to be spontaneous at lower temperature. At lower temperature, since it's spontaneous, delta G would be exothermic, it would be negative. So the same thing which we already know, I know that it's spontaneous at lower temperature. At lower temperature, ice will form, right? So I was able to predict the exact same thing using this equation. Is this clear, this thing?
Yes.
That I was able to figure out the same thing. It was pretty obvious, but I was able to figure out using the equation. Now I'm going to give you a reaction whose spontaneity you won't be able to figure out. Like, let's say burning octane. Octane is your fuel. That's C8H18, right? So let's say burning octane burns. And let's say it produces, it's going to produce 8 CO2 molecules and 9 water molecules, I guess. And that's 9 and 8, 16, 20, 12.5 oxygens. So 12.5 oxygens. And let's say this is also being produced in gaseous state. Just hold on, just give me 1 second. So this example. Now that's burning of petrol, right? So I want to figure out whether it's going to be spontaneous at higher temperatures or lower temperatures or all temperatures. When will this reaction be spontaneous? That's what I want to figure out. So what do you think the enthalpy change is for this reaction? This is combustion.
Negative.
So it's negative, right? What do you think the entropy change is? Is it an increase in disorder or decrease in disorder?
Increase in disorder.
Increase. So that's positive, right? There's a gain of disorder. So I'm now going to try and figure out when will this reaction be spontaneous. So delta G is equal to delta H minus T times delta S. Now, enthalpy change is negative. Entropy change is actually positive, right? So this term is negative. Delta S was positive, but it's got a negative sign in front of it. So this side is also negative. So both terms are negative. So delta G in this case would always be negative. Is that clear? It's always negative. There's no possibility of it ever coming out to be positive. So what does that indicate? It indicates that this reaction, burning of octane, is feasible at low temperatures. It's also feasible at high temperatures. It's going to be spontaneous always. Is that clear, this one?
Yes.
Okay, so we can do another reaction. Another example, let's have, let's talk about the Haber process, N2 plus 3H2 and 2NH3. The delta H is negative for this. It's minus 88 something. What do you think is delta S for this? Positive or negative?
Negative.
Okay, that is negative. Now I want to figure out whether this reaction will happen at a lower temperature or a higher temperature. So delta G is equals delta H minus T delta S, and both of them are negative, right? So this is negative and this is negative. So this side would actually become positive, and this side is actually negative. So if I want to make delta G negative, spontaneous, T should be high or low? I mean, this term should be smaller, right? So how can I make it smaller? I can make it smaller by having a lower t, a smaller t. And that is when the reaction will become spontaneous. So this reaction will happen at a lower temperature. It's going to be favored by a lower temperature. Is this clear? Is
Yes.
this? And we can kind of make a table for this because there are like 4 combinations. We can come up with a table. That table would give us an idea of what would be delta H. When would a reaction be spontaneous? So I've got delta H and I've got delta S, and so I'm going to figure out how can I make the table. That's let's say the first 1 second. There are going to be 4 combinations. Okay, so I've got these. I'm going to put in 4 values. So first one, both of them are positive. So when will it be negative? We did an example over here, but when both of them are positive, right? I guess we did. Did we do an example where both of them are positive? No, we didn't. Gain of disorder and it's endothermic as well. Endothermic, and so I'll give you an example for this. What if both of them are positive? So let's try, I think, a decomposition reaction. Is it endothermic or exothermic, this one? Calcium carbonate decomposing to form calcium oxide.
Endothermic.
Because that is endothermic, right? So it's delta H is positive. What about delta S? Is this a gain of disorder or loss of disorder?
Negative.
There's a gain
It
of
is positive. It is positive.
Positive. Both of them are positive, right? So when you think decomposition will happen, it will happen at a higher temperature. So we can justify that by using the Gibbs free energy, which is delta H minus T delta S. So one of them is positive, and the other one is also positive, but because there's a negative sign, this side would actually become negative. Now, in this case, if I want to make delta G negative, right, I need to keep the negative term bigger in size, right?
Temperature should be high.
So T is higher. So decomposition will happen at a higher temperature. It's going to be feasible at a higher temperature, and it's not going to happen at a lower temperature. So the first one, delta G, that's just making the table, filling up the table. That's so negative at higher temperature, right? So hopefully, so negative at higher temperature. What about let's fill up all the other values, positive and negative. We did all the other examples. This one negative, this one positive, and both of them being negative. So I'm just going to copy what we figured out. If both of them are negative, it's going to be, you need a lower temperature, right? So it's going to be negative at lower temperature. So that's this one. If delta H is negative and this is positive, delta H being negative, this is positive, it's then it's always negative. So this one over here is always negative. And then there's another one, which is this one. This one actually is never negative. It's always non-spontaneous. I can't really think of a reaction. Can I? So disorder, enthalpy change is positive and disorder is decreasing. Can we come up with an example? I mean, I'll just Google one. Reactions non-spontaneous at all temperatures. So if we can a reaction that is non-spontaneous at all temperatures. Just checking if they have. So I guess I'll fill up with an example. I can't really come up with an example at the moment. A reaction that is always non-spontaneous. So it's never going to happen. So it's basically not a reaction. But remember this one. If delta H is positive and delta S is negative, this particular reaction, it can never actually give you a negative value for Gibbs free energy. So this reaction will never going to happen. It's never going to happen. Is this clear?
Yes.
Achha. So the very last thing, same equation. The very last thing is you can put in values in this equation. That's the last thing. You'll be asked to calculate, do calculations based on this. So just plug in values. So that's the last thing. And I'll just do some questions from the values into delta G. Into this equation, delta G is equal to delta H minus T delta S. Now, you'll be given three things. You'll be able to figure out the fourth thing. So what will be given is that you might be given Gibbs free energy, and you'll be asked to figure out enthalpy change. Temperature would be given. So three things would be given, and you'll be asked to figure out the fourth thing. So there would be easy questions, but a lot of questions would be about spontaneity. They'll ask you, they might ask you to just calculate Gibbs free energy. So they'll give you enthalpy change, they'll give you temperature, they'll give you entropy change, and you figure out Gibbs free energy, and that's it. But there's one question which would be very specific, and that would be that when or at what temperature is the reaction spontaneous? And remember, it's always a very specific temperature. At a very specific temperature, the reaction all of a sudden becomes spontaneous. Like boiling water, when is it spontaneous? It's spontaneous above 100 degrees centigrade. Below it, it's not spontaneous. So there's a very specific temperature at which all of a sudden the reaction becomes spontaneous because it's got Gibbs free energy, it's got excess energy, and it doesn't need energy from outside. So how do you figure that out? So how would you calculate this temperature? You know that for a spontaneous reaction, Gibbs free energy should be less than 0. And what is the Gibbs free energy? Gibbs free energy is equivalent to delta H minus T delta S. So that means delta H minus T delta S must be less than 0. And you're going to solve this inequality. Is that clear that if they ask you to figure out at what temperature is the reaction spontaneous, you know that for a spontaneous reaction, Gibbs free energy should have a negative value. That means delta G should be less than 0. And what is delta G? Delta G is delta H minus T delta S. So that means that should be less than 0. And you just solve this. Is this clear? Is this part clear?
Yes.
So
Yes.
okay, so just remember this part. It's the same equation. You just solve it like an inequality, and you'll find the temperature at which the reaction would be spontaneous or non-spontaneous. So we'll do a couple of questions, and let's try and do Gibbs free energy questions. It's always a range. Like if I say boiling water is spontaneous, it's spontaneous above 100 degrees centigrade. So that's a range. It's never one temperature. It's always a range. So for example, let's do a similar question. For example, is this about Gibbs free energy? So yep, this is. He's saying calculate the minimum temperature, this part. So what he's saying is calculate the minimum temperature. This one, part C. Calculate the minimum temperature at which this reaction becomes spontaneous. So for it to be spontaneous, the delta G got to be less than 0, right? And what is delta G? Delta G is equal to delta H minus T delta S. So that means delta H minus T delta S must be less than 0, right? And you're given these values. You're given the temperature is the only thing that you don't know of. So delta H is 130 kilojoules. Minus T is not known. And focus on this. This is in kilojoules. This is in joules. So make sure you turn this into kilojoules as well. It's going to be 316. And that's going to be divided by 1000, right? And that's less than 0. And then what you're going to do is you're going to solve this. So what you have over here is that it's T times 316 100, that's got a minus sign, less than 130. So I'm going to bring these terms over here. It's going to be into 100. And it's going to be divided by 316. It's got a negative sign as well. Now, also remember for inequalities, if you want to get rid of the negative sign, the inequality direction will change. So T is basically greater than 130 times 100 divided by 316. Is that clear? This one. And give me the answer to this as well.
Sir, is it divided by 100 or 1000?
Yeah, 100 by or 1000. It must be 1000, I think.
1000, yes. Yes. Okay. What do you get for this? And this part, remember this, that if you get rid of the negative sign or you multiply by negative values, the inequality sign, it changes direction. For example, 3 is smaller than 5. But if I multiply it by -1, then -3 is actually the bigger one. So remember this, that multiplying it by a negative number would change the direction of the inequality. So what do you get for this? Somebody
111.39.
So you can say that it's well, let's say 412 or 411.39 to be more precise, but make sure that you write numbers up till the appropriate significant figure. So I guess it's going to be 412. I'll check the MS for this. That's I mean, they've accepted that, but 412, that's also given as an answer. And then you've got this question as well, like explain with reference to delta G why this reaction becomes more feasible at higher temperatures. So I guess this is the same as the whole predicting thing. It's minus T delta S, right? Delta H has got a positive value. And delta S, what is delta S? We didn't know, we don't know what delta S is, so we can actually calculate it. Product minus reactants. What do we get for this? It's what's the product? It's CO2, that's 214. So that's CO2, and you got NGO, that's 26.9. And I'm going to subtract the reactant, which is MgCO3, that's 65.7. So I guess that is positive, right? So one of my terms is positive, the other one is actually, it's actually negative, right? Okay, so that's 175.2. But anyways, he's 175.2, right? I'm talking about part 2 at the moment. So explain with the reference to delta G why this reaction becomes more feasible at higher temperatures. So if you take a higher temperature, what happens to the negative side? It actually becomes more negative, right? So you're going to write that at higher temperatures, minus T delta S, it becomes more negative, right? Hence, delta G becomes more negative. I mean, that's it, probably just 1 mark. So that's why the reaction is becoming more feasible. And if you want to calculate delta G, you just have to plug in the values. The enthalpy change is given, that's 117 minus T. What is T? That's 298 Kelvin. Should always be in Kelvins. Into delta S, the delta S must be in kilojoules or make the unit consistent. So it's going to be 175.2 divided by 1000. So I'll be able to figure out what delta G is. Is that clear?
Yes.
And that pretty much sums up. I mean, for example, this question has all 3 components about delta G. You'll be asked to calculate delta G. You'll be asked to predict what happens to delta G, whether it becomes more negative, more spontaneous, or whether it becomes more positive. And you can be asked to figure out the temperature. So things like this. So most of these questions are kind of, for example, this one is also a calculation question. So what is meant by the term entropy? That's the disorder. It literally means disorder of the system or the reaction. I mean, this is the definition that's given. It's a measure of the disorder of a system. I mean, that's given in brackets. You can write the whole thing. So calculate the standard entropy change for this reaction. So again, it's the same thing, product minus reactants. And then he's asking, calculate the Gibbs free energy for this reaction at 25. So at 25 degrees centigrade. So enthalpy change is given. Can you calculate entropy change for this reaction very quickly? What is it? It's product. It's 214 into 3 plus Fe. That's 27 into 2 minus my reactants. That's 90 plus the other reactant, which is CO. That's 198 into 3. What do we get for this?
12.
So delta S comes out to be 12. And I'm going to calculate Gibbs free energy now. Delta G is equal to delta H minus T delta S. Delta H is given, that's 43.6 minus 43.6. So minus 43.6. So delta H minus T delta S. This should be in Kelvin. So that's, I guess, 298 Kelvins. Minus T times delta S. That's 12. But that's in joules. So you're going to divide that by 1000 and you'll get delta G. What do we get for that?
Minus 47.176.
Minus 47.17. Let's make it 2. It's 3 significant figures, right? I guess if all the values were accurate up till 3 significant figures. So we'll keep our answer to, and we'll check the answer, 47.2, right? Yep, we got minus 47.2. Make sure you remember this, that don't exceed the significant figures. Use the significant figures that are given in the question. And then you have a similar question. Why a temperature of 1000 is usually used for this reaction, even though the reaction is spontaneous at 25. So I've got delta. I'll first check whether the reaction is spontaneous or not. So delta S was positive, right? And what was delta H? Delta H was negative, right? So this kind of reaction is always spontaneous, because this term would also become negative, right? So both terms actually happen to be negative. So this one is always spontaneous. So the question isn't really about spontaneity. Why do you prefer a higher temperature? Because it's already spontaneous.
Maybe the rate of reaction, sir?
Exactly, the rate of reaction, because remember, it's not just a reaction being spontaneous. You need other things as well. Is it going to happen at a fast rate? Like if I want to freeze ice, right? Ice can freeze at -1 degree centigrade, but if I want to do it quickly, I'll prefer a freezer which has a temperature of -20. I want things to happen quickly. Plus, there's activation energy as well. Some reactions, like burning a match, is a spontaneous process. Burning wood is spontaneous, but it's got activation energy. Like if wood is burning at room temperature, it burns. Like if you want to burn paper, it burns spontaneously. But at the very beginning, it needs some activation energy. So there are two things why reactions need energy. Either you want to speed up the reaction, that's one, or the reaction requires some minimum activation energy. Is that clear? And is this point clear that a spontaneous reaction does not mean that it will happen on its own? Burning paper is spontaneous. You light a match, you can burn entire papers, they will burn spontaneously at room temperature. But right at the beginning, you would need some form of minimum amount of energy that would be needed to start the reaction, right? So two things why reactions need energy, and you can, we can check. It's either going to be rate, both. Either it's activation energy or it's the rate of the reaction, right? Is that clear? Is this clear? So and remember, it's not that difficult. This one is a very small topic. Just calculations involving Gibbs free energy, entropy change, and just predicting the sign of entropy change or predicting the sign of delta G. That's about it. And that pretty much sums up. There are a couple of questions, but those questions, a couple of difficult questions. But those questions are not really related to, for example, even in this worksheet, I'll share the worksheet with you. Even in this worksheet, these questions are more to do with polymerization. So they're kind of linked with the organic chemistry. So that's why these questions, some of them might be slightly difficult, but because they're not exactly entropy questions. So I'll send you an assignment on this later. And if does anyone have any questions?
Sir, can you share the notes also?
I'm going to share the board link. Okay. I can convert them into notes as well. 1 second. I think it's the same board link.
Is the class over?
Yes.
All right, thank you. Hafiz.
Okay, Hafiz. I've shared the board link. All the notes are there. You can either take a screenshot of the board, or I think there is an option to. I'll send the PDF as well for this later.
So how could we get these questions actually? Because for practice or for having a record?
I'm going to actually send them.
Okay, thank you.
I'll send it as a worksheet, as an assignment. I'll send those questions.
Okay, thank you. Okay, thank you. Allah Hafiz.
Thank you.